So number 45, we've got a satellite of mass 200 kilograms is launched from a site on the Earth's equator into an orbit 200 kilometers above the surface of the Earth. A, assuming circular orbit, what's the orbital period of this satellite? Well, again, remember, for things in orbit, the centripetal force is equal to the force of gravity. In this case, we're looking for the period and we know the radius. So for centripetal force, I'm going to take the mass of the satellite times 4 pi squared r over t squared. Again, this equation here involves both radius and period, and so I'm using this for centripetal acceleration this time to be able to solve it. And then the gravitational force, just g times the mass of the Earth times the mass of the satellite over r squared. Mass of the satellite cancels. Sorry, I used two different m's on this, but same idea. And rearranging the equation, moving the r squared to the other side, moving t squared to the other side, dividing both sides by g times the mass of the Earth, gives us this equation. Plugging in our numbers, please remember that the radius in this case is the sum of the radius of the Earth plus the altitude of the orbit, which is that 200 kilometers or 200,000 meters. G and mass of the Earth, plugging in there. Don't forget to take the square root at the end, but you'll get a period of about the 3 sig figs, 5,310 seconds. B, what's the satellite's speed in this orbit? Well, I'm going to use the most simple equation, just the circumference divided by the period. Since we know the radius and we know the period, again, don't forget to add the radius here plus the altitude of that satellite over the period we just found, and you'll discover that it's moving at about 7,790 meters per second. Part C, what's the minimum energy required to place a satellite in the orbit, assuming no air friction? Well, this one's a little bit more complex. It starts out with both gravitational and kinetic. You might say, wait a second, it was on the ground. Well, it's at the equator, and so it actually is already moving with the Earth itself. So it has some kinetic energy. Plus, the work to put it in orbit is going to give it a new gravitational potential energy at the new height, and a new kinetic energy based on its new, now larger velocity. First of all, a little bit of work. How fast is it moving at the equator? Well, just plug in the radius of the Earth and the period of one revolution, 24 hours, 86,400 seconds. You'll discover it even at the equator, just sitting there at the launch pad, it's already moving 464 meters per second. Using those numbers, we can now plug it in. And I know, my apologies. So for gravitational potential energy, negative g m1 m2 over r, this is before its launch, it's at the radius of the Earth, plus its kinetic energy at that point, 1/2 mv squared, where this 464 is coming directly from up here. Plus any work done, and then when it's in orbit, its gravitational potential is going to be this, r has changed, and its kinetic energy is going to be this based upon the velocity it's going to have in orbit. Doing the math separately this time, just because I can't do it, you can calculate the GPE and KE for both of these. And then finally solving the work, just doing the algebra, the last part, you'll discover the work required to put in orbit is 6.42 times 10 to the 9th joules. By the way, if you're curious, notice that is almost just the gain in kinetic. If you compare it here, there's a slight change in gravitational along with the increase in kinetic. This part right here is so small compared to the other terms, it's almost negligible. So we could have probably ignored the kinetic energy due to the rotation of the Earth without really changing our final answer. I hope this helps.